All right, here is question number 1, where it talks about a species of plant that is spreading. It talks about the number of acres affected by the species, and then also gives you C prime for the rate of change of the number of acres. So part A says find the average number of acres affected. So for average number of acres affected, well, the number of acres affected is C of t. So if we're finding the average of C of t, then we're going to use our average value for C of t, which would be 1 over b minus a times the integral from a to b. So 1 over 4 minus 0 times the integral from 0 to 4 of C of t. We're using C of t because that is the amount function that we're finding the average value of. And then put that in the calculator, and we get our answer of 2.78. For part B, it wants to know when the average rate of change is equal to the instantaneous rate of change. So for our average rate of change, we use our f of b minus f of a over b minus a. That's our average rate of change, and we want to know when that is equal to the instantaneous rate of change. Now, the instantaneous rate of change is C prime, is the derivative. That's the instantaneous rate of change. So we want to know when the derivative equals that value that we found for average rate of change, the 1.282. So we're going to set C prime equal to the 1.282, to that average rate of change, and we want to find what value of t that occurs at, which, looking in your graph, is 2.154 weeks. Over in part C, we are continuing to spread, and we want a limit that talks about the end behavior. Now, end behavior tends to be limits as we approach infinity. So if we want the end behavior of the rate of change, and then we want to evaluate it, then we are going to find the limit of C of t, or C prime of t, of the rate of change of it. So we want the limit as t approaches infinity, end behavior, of C prime, the rate of change, which is 0. That is because this degree on the bottom is bigger. So as t gets really, really, really big on this function up here, that 25 plus t squared is going to get bigger and bigger and bigger and bigger. The 38 is going to stay 38. And we have 38 over this really huge number, which will get closer and closer to 0 as t gets larger and larger. So that's why that limit is 0. And you can also see that on the graph, that horizontal asymptote going closer and closer to 0. Over in part D, we get a function for a of t, for the number of acres affected by the species, and it asks at what time does a attain its maximum value. So if we're looking for a maximum for a of t, well, for a maximum of a of t, we look at a prime. And we're going to set a prime, which the derivative of c is c prime, and the derivative of the integral is the original function. That's fundamental theorem of calculus. So then we are going to do a prime. We're going to set that equal to 0. And check that at that value we are also changing from positive to negative because we want it to be a maximum. We're going to compare that to the endpoints. So our endpoints are 4 and 36. So a of 4 is c of 4 minus, this expression will come out to be 0 at 4. So it's just c of 4. And then for plugging in 11.442 and 36, we just plug in those values into this expression. So we do c of 36 minus the integral from 4 to 36. And same thing for the 11.442. We're looking for the maximum. So the 11.442 turns out to be the largest value that we have of 7.317. So that is the time, and we're reporting what time it happens That's the time where the maximum gets attained. On to number 2. Number 2 is your areas and volumes question. It gives you a function. This is our region R, our 2 different graphs. And we are going to start with find the area of the region R. Show the setup of the calculations. So G is our top curve and F is our bottom curve. So if we want to find the area of R, then we do our top curve minus bottom curve. Here's my recreation of the drawing. If we want the area of R, our integral goes from 0 to 3, because that's our left and right endpoints of the boundary. And then the top curve is g of x minus the bottom curve is f of x, dx. And then put that in the calculator, we get our answer. For B, it says region R is the base of a solid. The cross section is a rectangle with the height being x and the base being the region R. We're going to find that volume. So if we're going to find that volume, we have area of a rectangle is base times height. The base is the part that's in the region, so that's still our top curve minus bottom curve, g of x minus f of x. For our height, it says the height is x, so we don't need to do anything else fancy with it. We're just going to put h equals x, our height equals x. So that means our integrand, our part inside of there, is the area function. So we have our base, g of x minus f of x, times our height is x dx. And we're still going from 0 to 3. And there we get 7.705 when we put that into the calculator. Part C. Write but do not evaluate an integral expression for the volume around y equals negative 2. So y equals negative 2 is a horizontal line that is underneath this graph. So this is going to be a washer. So we've got pi times big R squared minus little r squared. And if we look at our drawing, big R goes from the edge of g of x down to that negative 2. So we're going to subtract those, g of x minus the negative 2. And then for our little r goes from f of x, our curve, down to negative 2. F of x minus negative 2, which is where these pluses happen, the minus and negative. Don't forget your pi out in front, times your integral is from 0 to 3 of that big R squared minus little r squared dx. Then it says here's g prime. I mean, you could evaluate that out by hand, but it gives it to you for the sake of time. It says find the value of x at which the line tangent to the graph is parallel to the line tangent to the graph at g. So if we see the question talking about tangent lines, hopefully your mind jumps right away to we're asking about f prime and g prime. And if we are looking for the tangent lines to be parallel, we remember that parallel lines, their slope should be the same. So if we want the same slope happening, then we want to know same slope, we want the derivatives to be equal. So we're asking, when does g of x equal f of x for the derivatives? So we want g prime to equal f prime. And so we're going to set those two derivatives equal to each other and find where they intersect. And again, we can go to the calculator and find that intersection point of 0.676. And that's question 2. Again, tangent lines are parallel when the derivatives are the same because we want them to have the same slope. Question 3. Here's our table. So the first part asks about average rate of change from 0 to 2 to approximate r prime of 1. So average rate of change, remember, is f of b minus f of a over b minus a. So we're going to do r of 2 minus r of 0 over 2 minus 0. And we have all those values laid out in the table. That'll give us 100 minus 90 over 2 minus 0, which evaluates out to 5. And since r of t was in words per minute, then r prime should be in words per minute, or words per minute squared. And we want to make sure, because the question asked indicate units of measure, we need to make sure those units are there. Then part B, it's asking whether r of c reaches 155. This is an intermediate value theorem question. So first we need to say, to use intermediate value theorem, we need to say that the function is continuous. So we're going to say that by saying that, hey, r is differentiable, and if r is differentiable, it's continuous. And so once we know that it's continuous, then we need to show with those endpoints, one of them needs to be below my target value of 155, and one of them needs to be above the target value of 155. And looking at the table, at 0, we're at 90, which is below 155, and at 10, we're at 162, which is above 155. So we start below 155, we end above 155, therefore, at some point, we have to cross through 155. That's intermediate value theorem. For part C, we're using a trapezoidal sum to approximate integral from 0 to 10. We got to be careful here because the subintervals are not the same each time. So we need to use the different subintervals. Remember, it's h over 2 times base 1 plus base 2. So for the first interval, h is 2, because it goes from 0 to 2, so that's a distance of 2. And then the bases are those y values, so 90 and 100. For the second trapezoid, the base is 6, because we're going from 2 to 8. That's a base of 6. And then 100 and 150 are the two bases. And then height of 2 again, because we're going from 8 to 10. And then there's your two bases. Put all those together, and we get 1,252 words. Finally, we are given W of t for the teacher, the rate that the teacher's reading, and it asks how many words has the teacher read by the end of the 10 minutes. Well, they're starting reading at t equals 0, so there's no starting condition to think about. So we just, we're given the rate that they move, and we want to know how many that's accumulating, so we're going to take an integral from 0 to 10 of W of t. And so this requires a little bit of working through by hand. The 1/3 that would come out in front of the antiderivative here cancels out with the 3/10 to make it the 1/10. And then it would be 8 times 1/2 t squared, so that makes 4. And then antiderivative of 100 is 100t. Plug in 10 minus plug in 0, you get 0. And then plug in 10 gives you 1,300. And once again, the teachers are victorious, as always. Moving on to number 4. We are given this continuous function. This is the graph of f. And then it goes on to talk about that g is the integral of f. And in any problem, when it says that g is the integral of f, the first thing you should make note of, maybe at the top of your paper, top of the question, if g is the integral of f, then the first thing I'm going to write is that g prime is f. And we want to say that in our explanations, because they're going to be looking for that at some point in the explanations. So I put stars by it to say, hey, this is important to say that g prime is f. I also went ahead and computed some areas up here within the picture. We've got some semicircles to do 1/2 pi r squared. We also have a triangle that we're going to use 1/2 base times height. So I've got some areas that I can use if I need to evaluate g. In part A, they tell you to find g prime of 8 and give a reason for our answer. Well, our reason of how we know what g prime is because g prime is f. So if I want g prime of 8, well, g prime of 8 is f of 8. And if I count along my slope, I can find that that f of 8 has to be 1 if we're going up along the slope of, if we're going up along that slope, which is 1/2. So f of 8 has to be 1. Find all values at which g has a point of inflection. Give a reason for our answer. I always like to start with the explanations here. Our explanation should have to do with the graph of f. So if I want to know when g has a point of inflection, that means I'm looking for, I have g prime in front of me. I want g prime to have a maximum or a minimum. Or in other words, I want g prime to change from increasing to decreasing, because that'll tell me that g double prime, that second derivative, will equal 0 and change sign. So that happens at 3 locations. My max and min on this graph is at -3, +3, and +6. Those are the locations that I'll have a point of inflection on g. Part C, find g of 12 and g of 0. Oh, here's where my areas are going to come in handy. G of 12. We're going to find the area integral from 6 to 12. Starts at 6. So from 6 to 12, we are going to do area of that triangle, which was 9. So that is our integral from 6 to 12. For g of 0, we go from 6 to 0. Now, I like to change those bounds, since those bounds are kind of backwards from how they usually are. So I'm going to switch those bounds. When we switch those bounds, we got to change the sign to be negative. That's where this negative sign comes from. And then I had already computed the area up here to be 9 pi over 2. So with that negative in front, it makes it negative 9 pi over 2. Finally, in part D, it says find the value at which g obtains an absolute minimum on the closed interval. So we want an absolute minimum. Well, if we want g to have a minimum, then g prime, which is f, we're going to say it again, that g prime is f. We want g prime to change from negative to positive, which happens at 0. So at x equals 0, that is our candidate for a minimum, and then we're going to compare them to the endpoints. So here's our endpoints. We have -6, we have 0, we have 12. Luckily, we already found g of 0, we already found g of 12, so those are done. We just need g of -6. And the way we can get g of -6 is because we have the integral from 6 to -6, which, if we look at these two areas right here are both the exact same semicircle that are going to cancel each other out. Being positive and negative, they're going to cancel each other out. And so that leaves that integral to still be 0. So between these 3 candidates for the minimum, the smallest is indeed at 0, negative 9 pi over 2. So that is my absolute minimum over the interval. Next up, question 5, is our particle question. So we are given the position of h and the velocity of j. So be careful that one of these is position and one of these is velocity. Here we go, part A. Find the velocity of h. Well, if I have the position at h, then to get the velocity of h, let's take a derivative. So the derivative of the position at h is the derivative of e to the t squared minus 4t, which is e to the t squared minus 4t, and then we use our chain rule to multiply by the derivative of that inside part. So times the derivative of t squared minus 4t is 2t minus 4. And it asks us to plug in 1, so we're going to plug in 1, and that gives us negative 2e to the negative third. That negative exponent is going to bring it down to the bottom. We get negative 2 over e cubed. Then for part B, we are looking at velocity. Now, velocity, we are looking for velocity being 0. The reason we're looking for velocity being 0 is we're looking for the motion of h and j. We want to know when they're moving in opposite directions. So we do our analysis and we find that at t equals 2, that's when the particle h stops. And then at t equals 1 is when particle j stops. And looking at our motion of h and j, we find that they're moving in different directions between 1 and 2. The rest of the time, they're moving in the same direction. They're either both moving to the left or both moving to the right. But between 1 and 2, h is moving to the left, and then j is moving to the right. So therefore, they're traveling in opposite directions. Part C, we are told that the derivative of the velocity of j is greater than 0. Now, you should know that the derivative velocity is acceleration. So this is telling you that acceleration is positive, and then we're asking, is the speed of j increasing, decreasing, or neither at t equals 2? Well, we already know and already decided from earlier that velocity is positive at 2, and then we're told that acceleration, we're going to connect that velocity v prime to acceleration, is positive. Therefore, we are moving to the right, and we are also being pulled to the right with the acceleration. So acceleration and velocity have the same sign, therefore the speed is increasing at t equals 2. And finally, for part D, it gives a starting position at t equals 0 for particle j, and then it says give the position at t equals 2. Well, it's time for an integral, because we've got the velocity of j. We're going to use that starting position of 7, and then define how much it moves between 0 and our point. We take an integral. So it's going to be 7 plus the integral from 0 to 2. And the best way to do this antiderivative is with a u substitution. That x squared minus 1 is inside of another function being cubed, and the derivative of that, which is 2x, is elsewhere in the problem. So we can do this replacement. Here's my substitution. I'm going to take this stuff right here and replace it with du. I'm going to take the stuff right in here and replace it with u. Now when I do that, I need to make sure that I change my bounds. So instead of going from 0 to 2, I'm going to put that into the x squared minus 1, and I'm going to go from 0 squared minus 1 to 2 squared minus 1, which tells me that I'm now going from -1 to 3. And then evaluate out your antiderivative becomes really simple now, and the evaluation becomes quite a bit quicker as well, and we get 27 as our position. Question 6 gives you an equation implicitly, and then asks you to show what dy dx is. So we're going to do implicit differentiation here. And it already tells us what the answer is, so we know what we should get. No fancy product rules or anything to worry about. So we're taking our derivative of y, we put a dy dx. We collect everything with dy dx and keep it on the left side. Anything without a dy dx gets kicked over to the right side. I'm going to rewrite -1/2 x as -x over 2. Now that all the terms have a dy dx on the left side, we can factor that dy dx out. And then we're going to divide to have dy dx by itself. And would you look at that? It's the answer that they said it was. How convenient. Part B. There's a point near 2, -1 with an x-coordinate of 1.6. And we're going to use the tangent line to approximate the y-coordinate. So first we need the tangent line. So it's time to use that derivative we just found to get our slope of that tangent line. So dy dx at 2, -1 we're going to put in 2 for x. We're going to put negative 1 for y into the answer that we just got. And we get negative 1/4. That becomes the slope in our tangent line equation. So we go y minus our y coordinate of negative 1 equals our slope is negative 1/4 times x minus the x coordinate of 2. That's our tangent line. And we're going to use that tangent line to approximate at 1.6. That's what the question asked us to do. So put in 1.6 for x, and then see what value we get out for y, and we get negative 0.9 as our approximation. Next is part C. We are asked in the first quadrant, x greater than 0, y greater than 0, there's a point where the line tangent to the curve is vertical. So if we want the tangent line to be vertical, we're still asking about the derivative because it's talking about the tangent line. And if we want it to be vertical, let's think about that slope. In a vertical line, the slope is going to be undefined. So we want to know, where is the slope undefined? So we are going to look for where dy dx doesn't exist. And if dy dx doesn't exist or is undefined, that's going to happen where the bottom is 0. So I'm going to take the bottom and I'm going to set it equal to 0. And fortunately, that factors. So we get 2 answers of negative 1/3 and positive 1. And we look at negative 1/3 and we cross it out because it's not in the first quadrant. So y equals 1 is our value. We don't need to do anything else with it because it just asked where the y coordinate was, and that was it. Then over on D, it gives us a new curve, and this is a related rates question. So it gives you dx dt, and it asks for dy dt. Now we've got a product rule going on. It tells you at the point 4, 1, so x is 4, y is 1. It gives you dx dt is 3, and it asks for dy dt. So here comes your derivative. So I'm going to leave the 2 out in front, and then x times y is a product rule. So x times dy dt plus y times dx dt. That's your first times derivative of the second plus second times derivative of the first. And then derivative of natural log of y is 1 over y. It's the derivative of y, so we write dy dt. And then derivative of 8 is 0. And now we can put everything else in and solve for dy dt. So the rest is just algebra and plugging things in. We're trying to get dy dt by itself. So I combined 2 times 3 is 6. So that's how we wound up over here. I distributed the 2. 8 dy dt plus dy dt is 9 dy dt. And then I subtracted the 6 from both sides to get negative 6. Divide, and we get dy dt to be negative 2/3 down as our final answer. And that is this set of FRQs.